Welcome to Precalculus. I am Mrs. Austin, your instructor, and I'm happy to have you in the course. This is the prerequisite chapter, Chapter P in your textbook. And in this chapter, we will be reviewing concepts that are necessary for your success in this course. Each video has a set of interactive notes with it. And at the top of one of the very first pages, probably the first page of your notes, you will see learning targets. And I am not going to spend any time reading through these each time you see these. They're just there to give you an idea of what's covered in the lesson. And this gives you also an idea of what you should be able to do once you've finished viewing the video and filling in your notes. So let's begin with a review of inequalities and also interval notation. When you first learned to graph inequalities, you used open and closed dots for the endpoints. We will be using interval notation to represent those same concepts. Interval notation uses, instead of an open dot, we use a parenthesis, and instead of a closed dot, we use a bracket. So let's go ahead and take a look at some examples of how we would graph and also write intervals. So letter A of the first example says 6 is less than x. Another way of writing that is x is greater than 6. Some of you might be more familiar or more comfortable with writing it that way, x greater than 6. If we do it that way, that says that all of the numbers bigger than 6 are solutions. It does not include the endpoint 6, so therefore we would have a parenthesis on the endpoint 6, and we would shade in everything to the right, all the numbers that are greater than 6. Our interval notation then would be 6, comma, positive infinity. And one of the things I want you to notice is that whenever you have infinity in your interval, it will always be a parenthesis. You'll never have a bracket on infinity. How about letter B? It says all the numbers that are less than or equal to 3. This one includes our endpoint, so that'll be a bracket on positive 3. All the numbers that are less than or equal to that are to the left. So there you see the graph and its corresponding interval. Letter C, we have two endpoints, 4 and 10. Anything that's bigger than 4 and less than or equal to 10. So this one has a boundary on both ends. The 10 is included, so it's a bracket. That would be equivalent to a closed dot. And the 4 is not included, so that would be an open dot or a parenthesis. And then your interval notation is indicated below. In letters D, E, and F, we want to graph the intervals on a number line. So the first interval, it says it does not include 4, but it does include 8, and it's all the stuff in between. So if we were to graph that, we would have a parenthesis on 4 and a bracket on 8 and shade the stuff in between. Letter E says everything less than 2, and it also includes 2 because it has a bracket. So we have a bracket on positive 2 and everything to the left. And letter F says anything greater than or equal to negative 3, so that would include a bracket and everything to the right. In this slide, we are going to use interval notation to describe the graphs. We're going to go backwards this time. And we have two endpoints here, A and B. A is included, B is not. So the interval that represents that would have a bracket on A and a parenthesis on B. This might be a good time for you to go ahead and pause the video, see if you can fill in all of these on your own, and then check your answers when you're done. All right, I hope you had a chance to try to figure those out on your own. Letter B does not include either endpoint, so both of those are parentheses. Letter C only has one endpoint. It is included, so that'll be a bracket on B, and it goes to negative infinity. Letter D does not include the endpoint, so that'll be a parenthesis on both sides going to positive infinity. E and F are a little bit trickier. Both of these have two intervals. So the left side interval would be represented by negative infinity to A, and A is not included. The right side interval includes endpoint B and goes to positive infinity, and it's the union of those two sets. Remember, we represent the union by the letter U, like a capital letter U. Similarly, letter F will have a bracket on A. It goes from negative infinity to A, and you're going to use the union of that set with the parenthesis on B to positive infinity. All right, so we have a couple of definitions we need to kind of go over, and we're going to have different types of intervals. We can have an open interval and an open interval does not include the endpoints. A closed interval is the opposite of that, and it includes the endpoints. And we also have what's called a half-open interval, which will contain one endpoint. So let's go back up to the problems we just did, letters A through C, and define whether those would be open, closed, or half-open intervals. Well, if we look at interval A, we have one endpoint included and one is not included. So it only includes one endpoint, so that's going to be a half-open interval. On letter B, neither endpoint is included, so that would be considered an open interval. And then on letter C, it includes endpoint B, so that would be considered a closed interval. So that's open and closed. Let's take a look at what other kinds of intervals we might have. We might have bounded or unbounded intervals. So a bounded interval has two endpoints, and it could be any of the three types of intervals we just discussed, open, closed, or half open. Similarly, an unbounded interval has only one endpoint, and again, it may be open, half open, or closed. So let's go ahead and take a look at what those look like, bounded intervals of real numbers. Well, here we have an example where it includes both endpoints. This is considered a closed interval. Its inequality looks like this, and here is its graph. So we have boundaries on both ends, and it's all of the numbers in between those two boundaries are included as solutions. The second example, neither endpoint is included, so that is an open interval. Here is its inequality and graph. Very similar to the one above, it just has open intervals on the end. And then the third one, we have a single endpoint is included, so that's half open. Here is its inequality and graph. And the last one is very similar with being half open, and the inequality and the graph are included. So what does an unbounded interval look like? Well, an unbounded interval, again, we said they could be open, closed, or half open. This is an example of a closed interval because A is included, and its inequality says that anything that's bigger than or equal to A. So it goes off to the right. It is unbounded on the right-hand side. So there's a boundary on the left, but none on the right. Notice with all of your bounded intervals, you have endpoints on both ends. It's just a very small segment of solutions. So the second example here is an open interval. The endpoint is not included. Very similar to the one above, but the endpoint's not included. And then the third and fourth examples are also provided. They just go to the left. So notice the unbounded intervals only have one boundary on one side. The bounded intervals have boundaries on both sides. So that's kind of what those look like. Some properties of algebra that we need to go through. You should be familiar with these already, so I'm going to go through them very quickly. First one is the commutative property, and the commutative property has to do with the order in which you add or multiply things. It doesn't matter what order you add or multiply numbers, you'll get the same answer. The associative property has to do with a grouping of numbers. So it doesn't matter how you group them, whether you're adding or multiplying, you'll get the same answer. The identity property tells you you're going to end up with what you start with. So if I start with a letter U and I add the additive identity, I'll end up with U. For multiplication, the multiplicative identity is 1. If I multiply any number by 1, I'll get it back. The inverse property gives you the identity. So for addition, we're going to use the additive identity. We want to end up with the additive identity of 0. If I start with U, what do I add to U to get the additive identity? I add the opposite of U. For multiplication, what do I multiply U by to get the multiplicative identity? Well, how do I get 1? You would multiply by the reciprocal. So that's the inverse property. It gives you the identity, whether it's the additive identity or the multiplicative identity. The distributive property helps us to get rid of parentheses and just simplify our algebra. And I think you're probably pretty familiar with both of those. So I'm not going to spend any time on those. Exponents. It's another area that it would be good for us to review. Exponents. The exponent part is the superscripted number, and it describes how many times the number is multiplied by itself. So in this example, n is the exponent. The base is the number that's always in regular script, and that's the number that gets multiplied by itself. So let's take a look at some properties of exponents that you should be familiar with. We will be using these very extensively in this course, so make sure that you understand each of these properties, and they're going to get fairly complicated fairly quickly. So make sure you know each of these properties of exponents. The first property says if you have a number, a base number to an exponent, and you multiply it by the same base to another exponent, that you're going to add the exponents. The second one says if you divide two numbers that have the same base, then you subtract their exponents. Anything to the 0 power is 1, no matter what it is. Anything to a negative exponent is equal to the reciprocal of the base number to the positive exponent. So there's an example there. Number 5 says that if you have two numbers multiplied together and they are raised to an exponent, everything in the parentheses gets raised to that exponent. Number 6 says if you have something to an exponent and then it's raised to an exponent outside of the parentheses, then you multiply the exponents. And number 7, if you have a fraction in parentheses raised to an exponent, everything in the parentheses again gets raised to that same exponent outside the parentheses. So let's go ahead and use what we just reviewed with our properties of exponents to go ahead and simplify some algebraic expressions. And we'll go ahead and start with letter A here. So letter A says 2 times x to the negative 1. Well, the negative 1 exponent is not on the 2, it is only on the x. So that's the same as 2 times 1 over x to the positive 1. And if we simplify that, we get 2 over x. Letter B, we have a fraction raised to an exponent. And our property told us that everything in that fraction then gets raised to that same exponent. So we would have 3 to the negative 2 power over x to the negative 2 and y to the negative 2. So now we need to deal with these negative exponents. A negative exponent says that it's the reciprocal of that. And rather than get into some very complicated fractions, the other way of thinking about a negative exponent when you have a fraction is that if it's in the numerator, it goes in the denominator and becomes positive. So the 3 to the minus 2 will be in the denominator as 3 to the positive 2, and that's 9. X to the minus 2 goes to the numerator and becomes x to the positive 2. Y to the negative 2 in a denominator goes to the numerator and becomes y to the positive 2. So final answer on that one is x squared y squared over 9. Letter C. This one, you have a choice. You can either multiply everything across or you can simplify within the parentheses first. I think I'll choose to simplify the parentheses first. So the 3 and the 2 are not going to simplify. They're going to stay there. But then we have a squared and a cubed. Well, the a squared will cancel. 2 of those a's will cancel in the numerator with 2 of those in the denominator, and we'll be left with 1 in the denominator. So we have a single a in the denominator. And then the b's are going to completely cancel out as well. So b over b is the same as 1. So the b's are gone. Then on the right-hand side fraction, the 4 is going to stay there. So we'll still have a 4 in the numerator. A to the 4th is not going to cancel with anything, so we'll leave it alone in the denominator. But then we have a b squared in the denominator and a b cubed in the numerator. So no more b's left in the denominator. They cancel out. And then we're going to have 1 b left in the numerator. So we still have a single b up there. Okay, now let's multiply these together into a single fraction. 4 times 3 is 12, and 12 divided by 2 is 6. That'll be in the numerator. We still have a b in the numerator. Denominator, we have an a in the left-hand fraction and a to the 4th, so we would add those numerators, or excuse me, add those exponents. So it would be a to the 5th power in the denominator, and that would be your final answer. And the last one over here, letter D. This one, we're going to go ahead and multiply the exponents. We have a power raised to a power. So in our fraction, we'll have x to the minus 2 times minus 2 is x to the positive 4. And then y to the minus 6, when you multiply a positive 3 and a negative 2. In the denominator, we're going to have y to the negative 5 and x to the positive 2. So now what I'm going to do is I'm just going to rearrange things a little bit here. I'm going to move the x squared on the left and the y on the right. And anything that's negative, I'm going to switch spots. So x to the fourth, I'm going to leave alone. X squared, I'm just going to move over to the left-hand side of the denominator. Y to the minus 5 will go up to the top and it'll become y to the positive 5. Y to the minus 6 goes down and becomes a positive 6. And now let's go ahead and simplify. Okay, so x squared is going to be gone. We're no longer going to have 4 x's up there. We're only going to have 2. Y to the fifth will be gone. And we're going to have a single y left in the denominator. So our final answer, when we clean that up, we're going to have an x squared in the numerator. And in the denominator, we'll have a single y. Scientific notation allows us to work with very large or very small numbers. And a number is said to be in scientific notation if the number is bigger than 1 but less than 10, and it's multiplied by an integer power of 10. So that's what all of this says. Your number C is greater than or equal to 1 but less than 10, and the exponent here on 10 is an integer. That means it could be positive or negative. You should be able to write numbers in both scientific notation and standard notation and be able to go back and forth. So here's a couple of examples. Let's work the first one together, and then you can do A and B on your own. So it says the distance between the Earth and the Sun is about 93 million miles. How do we write 93 million in scientific notation? Well, where are we going to put our decimal point for this number to be between 1 and 10? Well, the decimal has to be between the 9 and the 3. So that would be 9.3. And then the exponent on our power of 10, our decimal is at the end of the last 0. So we've gone 3, 6, 7 places. And since this number we started with is bigger than 1, our exponent is positive. If this number were a decimal number less than 1, we would have a negative exponent. So go ahead and work on A and B, and I'll show you the solutions when you get back. Alrighty, here's your answer to A and your answer to B. Hope you got those correct. If not, be sure to ask me in class. All right, lastly, this is our last slide, the last page of your notes. We can use scientific notation to help us estimate an answer without using a calculator. So if we were to do that in this problem, what we would need to do is just write each of these numbers in scientific notation. So there's each of those in scientific notation. Then what we can do is rewrite that, trying to get a single power of 10. So we're going to multiply just the whole number parts. And then the power of 10 that we end up with is 10 to the 10th power. And you should notice that 3.6 is twice as big as 1.8, so we will just get a 2, and 2 times 4.5 is 9. So that one you actually didn't need a calculator. Now moving it back to standard notation would be a 9 with 10 zeros. This concludes our first prerequisite section in this chapter on real numbers. We will see you next time.